Hello and welcome to lecture 18 on extrema and inflection points. So this is the first lecture in the third section of this class on the applications of a derivative. So we have in the previous section talked about how to take a derivative and how to characterize the slope of a function at any single point. Now in this lecture we're going to talk about how to use the first and second derivatives to find important points on the function f. All right, so I've started with this diagram here, which is an overview of extrema. So we start with this function f of x, and then we want to ask what is the derivative of f of x, and when is that derivative equal to 0? So if the derivative is equal to 0, then these are characterized as internal extrema, either maxima or minima of the function. All right, the alternative is that we have external extrema or edge extrema, which are the edges of the domain of the function. And we'll come back to that in a second. All right, so if we're over here in the internal extrema, so this is where that derivative is equal to 0, so it's either flat at the bottom of a curve or flat at the top of a curve, then we have to ask what is the second derivative. So if the second derivative is less than 0, then the way I like to think about this is that curvature, and it's less than 0, and it's a sad face, so it's curved down, and so that is the maximum of a function. So if you have a derivative of 0, but you have a second derivative that is negative, then you have the maximum of a function. If you have a derivative that is 0, and then the second derivative is positive, then this is a smiley face, and that is the minimum of a function. Now, this maxima and minima are only local, so you could have a curve that has multiple maxima and multiple minima, and some of them are going to be the largest maxima and minima over the whole domain, and some of them are just going to be a maxima or minima amongst the values that are close to them. So, if you're only then we characterize this as a local maxima or minima, and we can evaluate the function at all the maxima and all of the minima to ask what is the largest maxima and what is the largest minima. And this is where these edge extrema come in. So since at the edge of a function, at this point here, we can't take a derivative since it is only one-sided, we also have to ask whether those are the global maxima or the global minima. So we consider all the points where we can't take a derivative. So these are the edges of the domain, like that point there and that point there. But they can also include a point on the interior of the domain. If there's a sharp transition, this is known as a non-differentiable point. You could not take a derivative here since that derivative could be sloped at any angle and still match the function. And so if there's a sharp transition, like a V in the function, then this is also an edge extrema, and we evaluate the value of the function at all of those points, and we can characterize whether one of these internal extrema is the most extreme, or if one of the edge points is most extreme. All right, so this is just a summary, but we'll see how it comes into practice in the following example. There's one more point here, which is an inflection point. So if we have our derivative being equal to 0, we want to know if the second derivative is less than 0 or greater than 0. This determines if it's a maxima or a minima. But there are also cases where our function has a second derivative that is equal to 0. Note that the first derivative may be positive, may be negative, may be 0. But if the second derivative is equal to 0, this captures points where you transition from having a curve down to having a curve up. And these are known as inflection points. So for example, two examples of inflection point are shown here. So here the first derivative is also 0, and you go from having concave down to concave up at this point here. Here we have a switch in the concavity of the function, but the first derivative is negative. So whether or not the value of the first derivative is positive, negative, or 0, you can have an inflection point if the second derivative is equal to 0. So this is a transition in the sign of the second derivative, in the change in the curvature. All right, so let's characterize a function using inflection point. All right, so let's consider the function, this quartic polynomial, x to the 4th over 4 minus 2x cubed over 3 minus 5x squared over 2 plus 6x. Our first goal is to find all the critical points of f of x. So going back up to our diagram, finding the critical points are all of the internal extrema and the edge extrema. Okay, so how do we do that? Well, we first need to find the roots of the first derivative. So where is that first derivative equal to 0? All right, so the critical points are the roots of f prime of x. All right, so the first thing we need to do is actually take the derivative of f. So I want you to pause the video here and try to work this out on your own. All right, now that you're back, what is the answer? F prime of x is equal to, we use a bunch of power rules here to calculate this, and we have x cubed minus 2x squared minus 5x plus 6. All right, so now we have a cubic polynomial, and I've drawn that cubic polynomial here. So here we have, sorry, my apologies. This is the original function f of x as a function of x. And then we have just found the derivative of this. All right, so to find the internal critical points, we need to find the roots of this f prime of x. How do we do that? Well, we don't have an easily usable cubic equation like we do the quadratic equation. So the way to find the roots of a cubic equation are to try to factor the equation. Now, I'm going to let you know that you could factor this equation as x plus 2, x minus 1 times x minus 3. Now, I want you, as in your own work, to check this. So multiply these all together to show that if you multiply all of them together, you get back to this polynomial here. All right, but given that that is the way to factor this equation, we can then identify the roots of this equation. So this we're setting equal to 0, and we're saying, how does this function equal 0? Well, either this term is equal to 0, this term is equal to 0, or this term is equal to 0. So we have three roots here. Either x is equal to minus 2, in which case this term is equal to 0, x is equal to 1, in which case the second term is equal to 0, or x is equal to 3. All right, let's draw those 3 points on our plot. We have x equals minus 2, x equals 1, and x equals 3. All right, so we can see that those are either maxima or minima. In addition to those maxima and minima, we also have the external critical points, which are the edges of our function. So there are no internal transitions that are non-differentiable, so no v's. So we have only 2 extrema on the edges that are at x equals plus or minus 4. All right, so those are all of our critical points. Now we need to characterize those critical points as either local maxima or local minima. How do we do this? Well, for the internal critical points, we want to ask what is the second derivative at that internal critical point. So we want to know whether we have a minima, which is a positive second derivative, or a negative second derivative, in which case we have a sad face and we have a maxima. All right, so in order to do this, we need to find the second derivative. If you want to pause the video for a second and work out what the second derivative is, that would be great. Otherwise, we have that f double prime of x is equal to this quadratic equation, 3x squared minus 4x minus 5. All right, now we're going to plug in the second derivative at all of our 3 critical points. So the first one that we want to evaluate is f double prime of minus 2. If we plug this in, we get 3 times 4. Notice that you square that negative sign. Minus 4 times negative 2 minus 5. If you evaluate this out, you get 20 minus 5, which is equal to 15. This is greater than 0, so this is going to fall into this category here. It's a smiley face, so it is a minima. Local min. All right, what about our next point? Well, we have f double prime of 1. That's our next root. That gives us 3 times 3 minus 4 minus 5, and this comes out to being negative 6. This is less than 0, so that means that it is a sad face and it is a local maxima. Finally, we have f double prime of 3. If we work this out, we have 3 times 9 minus 4 times 3 minus 5, which comes out to being equal to 10. And this is greater than 0. So once again, this is a smiley face, and so this is a local min. All right, going back up to our figure here, we have that f double prime is greater than 0, which makes sense. It's a local minimum. Now we have f double prime is less than 0, and we have f double prime greater than 0. So it matches our plot up there. All right, so now that we have the critical points and the local maxima and the local minima, let's find the inflection points. What are the inflection points? The inflection points are the points where you have a change in curvature so that f double prime of x is equal to 0. So note when the function is equal to 0 are points where you have a transition in the sign of the function. When f prime, the derivative, is equal to 0, this is when you have changes in the slope. So you go from having a negative slope to a positive slope, so those are the maxima and minima. When f double prime is equal to 0, this is changes in the curvature of the function, so when you have things that go from concave down to concave up, or concave up to concave down, and so these are the inflection points. All right, so what do we have as our f double prime? We have f double prime is equal to 3x squared minus 4x minus 5. All right, how do we find the roots of this? Well, we have to use the quadratic equation. I'll let you use the quadratic equation on your own, but we have a quadratic equation, and this comes out to being x equals 4 plus or minus the square root of 16 plus 4 times 3 times 5 all over 6, which is equal to x equals either minus 0.786 or x equals positive 2.12. All right, so let's go look back at our figure and see if those look like inflection points. So if I go back up here at negative 0.786, that is going to be just slightly to the right of negative 1, and you can see that we have a curvature here that is concave up, and we have a curvature here that is concave down, so we do indeed have an inflection point around there. All right, the other inflection point is at 2.12, which is going to be around here. And once again, we go from being concave down to concave up, so we do indeed see an inflection point around there. All right, so now we have found the internal critical points, the local maxima and local minima. We found the inflection points. Let's go find the global maxima and global minima. How do we do this? Well, we have to evaluate the function at all of the internal critical points and the external critical points. So we have values such as f4, which is our rightmost edge over here, f4, and this comes out to being equal to 5.33. Okay, we have f of 3, that was one of our internal critical points. This is minus 2.25. We have f of 1, which is equal to 3.08. Then we have f of minus 2 is equal to minus 12.67, and we have f of minus 4. This is our other edge, but the left edge, and this comes out to being 42.67. All right, we already figured out that this was a local min, This was a local max, and this was a local min. All right, so that was from up above by using the second derivative. So this was f double prime. All right, now we can characterize these as global maxima and minima by looking at which is the smallest and which is the biggest. Well, this is our biggest point of all of them. So this is the global max. And this is our smallest point. So this is our global min. So now we have characterized the function completely using the function, the derivative, and the first derivative. And with that, I'm going to leave you with the self-study model, which is the Lie effect, which we've talked about numerous times, where you're going to go and you're going to take this function that we've talked about before, and you're going to characterize it using the first and second derivatives. All right, see you in class.